Welcome to the first seminar in the Thermodynamics 2.0 pre-conference series. Please mute your microphones and hold your questions and comments for the Q&A period. Please feel free to use the chat feature. We are recording this session and will post the video to the Thermodynamics 2.0 YouTube channel. Today we have the pleasure of listening to a talk by Terry Bristol. Terry is a philosopher of science and engineering who has held teaching positions at Linfield College, Portland State University, and Portland Community College. He has been the president of the Institute for Science, Engineering, and Public Policy and affiliated with Portland State University since 1987. See his website, terrybristol.org, for his book, Give Space My Love, An Intellectual Odyssey with Dr. Stephen Hawking. Now I'll hand this pretend microphone over to Terry.
Okay, so I'm gonna get this out of the way. Okay, so welcome everyone. This is what I'm going to offer you today is part of a larger research program on philosophy of engineering and the engineering worldview. And since it's large, so what I'm only going to be able to present for you here are some highlights of this, which I think will nonetheless give you the primary themes and understanding of what it's all about. And I'm not trying, I would say this, I'm not going to try and make any arguments here. I'm trying to convince you of anything. What I'm trying to do is introduce you to another point of view, another way of looking at some things that you may have been looking at differently. And mostly moving, if you like, from a scientific worldview to an engineering worldview. And as it turns out, the engineering worldview is also a thermodynamic view, so it's engineering thermodynamics. Okay, so I do this right now. It doesn't want to advance. Isn't that clever? There we go. Okay, so I just threw this one in. The difficulty lies not so much coming up with new ideas and escaping from the old ones. So to a large extent, my story of getting into philosophy of engineering and engineering worldview was really escaping from the scientific worldview. As Kuhn put it, we were all thoroughly indoctrinated in our education with that. So, okay, so what I'm going to offer today is that evolution and the organization of reality is only completely intelligible in terms of a participatory systems engineering thermodynamic worldview. That's a lot of words. So put it this way, what are we trying to understand? So I would put it into two things. How did reality come to be as it is? That's a sort of temporal evolutionary thing. But there's a flip side of that, which is the spatial version, and asking what is the spatial organization of reality? And I would call that, I'm going to suggest that the technological structures and functions of reality. So there's really two questions here. Often in evolution, we only talk about the temporal aspect, but it's also important that we understand that question of the organization of what actually did come to be. Okay, so corollary one, is simply that the structures and functions of reality, the organization of reality, if you like, as we understand it, or structures and functions are technological creations, okay, which is maybe surprising to some of you. And then I'm also, the thing is that reality cannot be completely understood in terms of any possible scientific worldview. Okay, so I'm going to put this in two parts. Part one is just, I'm going to introduce you to the modern philosophy of engineering and the engineering worldview. And then in part two, and that in part one is not so obvious that it's thermodynamics, which is the point. But in part two, then I'm going to go right after what is clarifying engineering thermodynamics, distinguishing it from the mechanical scientific version that we were all indoctrinated with, the Clausius-Boltzmann stuff. And then I'm going to look for the origin. Where did engineering thermodynamics come from? Where does it start? And I'm going to go back to Leibniz introduction of dynamics, and then my hero in all this is Lazare Carnot, Sadi Carnot's father, who made an attempt to complete Leibniz program and develop an engineering worldview. So he has started, George Biliarella, who's kind of a master engineer, a big deal, and he argued that engineers should be taught that engineering is a natural extension of biological evolution. Now, like maybe that's obvious. We came from, we were here, evolved, part of the evolution, but the implications of that are what's interesting. You're saying engineers are embodied participants in the progressive construction of reality. And what the implication is that evolution is now, but always has been, an engineering enterprise. The structures and functions of reality represent a recursively enabling engineering enterprise. So that's the idea. So he's saying, yeah, we're engineers, we're part of evolution, but then natural extension of evolution. But the implication is evolution is, in fact, and always has been, an engineering enterprise. And we don't understand what we mean by that. Now, this may sound shocking to some of you, but this is, in fact, not a new view at all. In Plato's Timaeus, reality is represented as the emerging design of the architecton, and that's translated commonly as the master craftsman. I think it's obviously as the master engineer. So Timaeus is asked, how did the world come to be as it is? And this is part of what he says. I'm going to make some other comments along the line, paralleling Plato's Timaeus, that engineering worldview, and the modern one. So what I'm suggesting from Bugliarello is that these embodied technologies, the world's made up like us, but it's made up of all these embodied technologies. And I'm going to say that they're also intelligently structured. An earlier version I gave of this, it looks at the early development of paleontology and microanatomy, where we started looking at the anatomy of organisms. And by and large, it's organisms are intelligently organized. The different parts all fit together and they work together. And that's what I mean by intelligent. And also that the parts that, as they are organized so that they can, the animals or the embodied intelligence can do things. So like the dog can catch the frisbee, the fish, so in other words, the intelligence is both is in the internal structure of the organisms and bodies, but is also intimately integrated with the how they act in the world and the way the world's organized. Here's some more. So all these count as embodied technologies. And the Earth itself, I'm going to say, is an embodied technology. This is the Gaia hypothesis, which I think is probably insightful. Okay, so now, second guy I'm going to go into here, I'm going to introduce this to you by going through 3 or 4 of the main players in modern philosophy of engineering review. Walter Vincenti is really crucial here. He really lays down a challenge to the scientific view of things. And in his book, What Engineers Know and How They Know It, he says here, I'll read it to you, modern engineers are seen as taking over their knowledge from scientists, and by some occasionally dramatic, but probably intellectually uninteresting process, using this knowledge to fashion material artifacts. He points out that from this point of view, studying the epistemology of science would automatically subsume the knowledge content of engineering. And then he lays it on you. Engineers know from experience that this view is untrue. So engineering knowledge is not derivative from science, but is an autonomous body of knowledge. Engineering is not merely applied science. Airplanes are not designed by science, but by art, in spite of some pretense and humbug to the contrary. The creative, constructive knowledge of the engineer is the knowledge needed to implement that art. So this is the basic challenge that Vincenti's saying. He's saying that essentially that engineering knowledge is autonomous, and in fact that science is, he said, I'm not against science. He said, we love science, but science is just tools. They're limited tools that we use in the art of creating things. Okay, so so he has different engineering, knowledge, engineering theory of knowledge, epistemology, also suggests an engineering ontology. And so, in other words, that then you have the engineering knowledge, and then you have the engineering world, what it's made of. And so I want to suggest that because engineers have this knowledge, and this knowledge is what they use to create the technological structures and functions of reality, engineers understand the structures and functions of reality in a way that is beyond scientific knowledge. Now, for instance, engineers understand like an airplane and the wings and the winglets on the airplane and why they're there and so forth. Those are things that science doesn't understand. And I'm going to give you one large hypothesis here that runs through all this, and that is the best image of the engineering ontology, what the world's made up of, is the engine. And it's the engine that is incomprehensible within the conservative scientific framework. You don't see engines in physics or, they're definitely there in biology, of course, because that's the biology all about. But anyway, the point is in, from a mathematical physics point of view, you don't have engines, and they don't have any way to make sense of engines. And I'll come back to this, but that's going to be one of the themes here. I say just basically the same thing. Engineers understand the reasons for things, the purposes for various structures and functions, the why and the what for. And I'm going to go, one of the things, if you look at that, the airplane there in the upper left, it's like the thing about the winglets, why would you need winglets on there? Is that something science would tell me about? No. It might use science to shape the ultimate thing on it, but the structure of the airplane and what it's doing and why we have airplanes and all that, these are things that engineers can understand because they understand the reasons for things. Why did I build it this way? Why did I build it that way? Look at the iPhone, all the different things in the iPhone. Why is this? Why is that? Those are things that the questions that don't make sense. Those why questions just don't come up in the scientific worldview. We're talking about what are the reasons that engineer, designs things one way or another. So its reasons and purposes are there in the engineering way of making sense of reality. So they would say, cities are embodied intelligent technologies, neighborhoods, government. This may be shocking. I'm not too sure about the intelligence of this, but that's the thing. I'm going to get into what do we really mean by intelligence, because I've given you a rough idea, but this is one of the main important things that we want to look at in engineering worldview. Okay, next guy is this guy, Sam Florman, a really, really, really important guy. Wrote a lot of stuff on in philosophy of engineering, and he has this great book called The Existential Pleasures of Engineering. And what does he mean by this? It's really nice. It's a very, somewhat philosophical book, because what he's connecting with is the continental existentialists of the last century, and so the existentialists had this idea that we find ourselves instantiated in reality with the ability to act, but we don't have any script to tell us how to act. Okay, now so the existentialists, so like they're not listening to the Pope anymore, or to anybody else. They're just this realization of their freedom, this existential freedom, and the existential character of it is it's just undefined, it's indeterminate. What am I supposed to do? Why would I have to do that? If any of you read Camus or any of those guys, so why would I have to go to my mother's funeral? I don't have to do that, do I? Why would I have to do that? So anyway, so what he points out, so what the existentialists, they found this was angst. They, like, oh my God, who am I? What am I doing? I'm lost. Florman turns it around and says, no, actually, this is really exciting. This existential care means I have options. As an engineer, I have creative options. I have free will. It's constrained, certainly, but I have this ability to act. And I have this creative opportunity to actualize the future reality. Now, in the Timaeus, when Timaeus is asked, how did the world come to be as it is? He says, well, I could only give you a probable account. And the reason this is important is because the existential character of engineering implies or entails that there are many, many paths to the future, many, many ways to create the technologies of reality. And so what Timaeus is saying eventually is that I can only give you a probable account of how we got to, if you look at the current technologies of modern 21st century Earth, are those the only way? Is that the only path we could have taken to create those technologies? So he's saying, no, it's not the only path, but he does say there is a path, which we'll get to. Okay, so the next guy, Herb Simon, is he's an economist, actually, a Nobel Prize economist, and he talks about engineering. This particularly a lot of books, but in this book, Sciences of the Artificial, and he tries to characterize engineering first. He says engineering is about problem solving. What is problem solving? He says it's to move from a current state of affairs to a more desirable future state of affairs. It's almost a tautology, you move from problem to solution. But this word desirable is really important, as this introduces us to the idea that there are values, considerations in engineering. And as Simon puts it, engineering is concerned with ought, what ought to be. And you think, science is about what is, and engineering is about what is ought, what ought to be, so to speak. You see that a lot. So one thing that Timaeus says, though, he says, and he says a similar thing, he says, maybe I can only give you a probable path of how the world came to be as it is, but one thing's for certain, that the world always moves to the good. Okay, so towards what ought to be, so to speak. Okay, we'll see that more. So the other thing that Simon, in characterizing engineering, we want to know, if the existential, if everything's existential, is it just chance? I mean, why am I choosing this way or that way? I mean, I don't have any script, so what is it? So is there an aim or an agenda, the overall long-term agenda in engineering? And Simon says, look at the problem of design. He said that's what engineers are concerned with, is design of something. And so you think, so how should we design the irrigation of our fields? It's agricultural design. How should we design our houses? This is architecture. How should we design our cities? I mean, we're talking about urban planning. How should we design our businesses? I mean, should we have this thing to the right is on Harvard Business Review? I'm sure you're all reading that, but it talks about the design, the evolution of design thinking. It used to be that design was something else, but now they're saying, wait a minute, questions of design that's about how I'm designing my business, my corporation, my whatever. Okay, and the same thing is, how should we design our economy? So the realization in the Harvard Business Review article is really about realizing that these questions of the economy and business structure and so forth are all design questions. Now, one step higher, we want to have a political system. How should we design our political system? Well, okay, at that point, in one sense, we're at Plato's Republic. Okay, how do we design our political system? That's what Plato's Republic's all about. Okay, so let's see, I'm getting ahead here. Well, the other thing is I want to say is the American Constitution. If you think of the American Constitution, is a design document. Okay, it's a document designed for an experiment of how we're going to live together. Okay, these are all design questions. In that sense, they're all engineering questions. Okay, so in the old conception of engineering as valueless applied science, I had a guy here from the National Academy of Engineering. Somebody asked him in the audience, he said, well, I know what science does. I mean, it's about discovery. What is engineers doing? He says, whatever they pay us to do. Oh, no, isn't the right answer. But so in modern engineering, the tools of science, here's the image, the tools of science are used to promote the values of a desirable world. Okay. So the engineering framework, I'm going to argue, is more general, and it subsumes and supersedes both the sciences and the aspirations of the humanities. So I want to say is that, I put it this way, the engineering framework is a bigger tent. It's more general. So we like science. Science is under, it's sort of a limited thing, but we like it. And the humanities are there. And all the concerns and debates and so forth of what is justice and so forth, those are all things that come under engineering, because the engineering context is in fact has a value saying. I'm going to just go over a couple of these real quick because these are just in the interest of time, so that you can ask me about these later if you want. So this idea of being more general, a couple of historical things, I would say engineering bridges C.P. Snow's two cultures. I don't know, a lot of people here, I'm an old guy. C.P. Snow's essay, Two Cultures, was about, this guy, he says, well, I have my, science friends, I have my humanities friends. My humanities friends can't tell you what the second law of thermodynamics is, and my science and friends have never read a Shakespeare. And he talks about there being these two cultures in our society. The one which is basically science oriented, and the other is humanities oriented. So what I'm saying is, what engineering is proposing here is that actually to bridge those two cultures. If we take engineering as the primary perspective, then we're happy with science and we're happy with humanities, and they both fit together under in an exploratory way, as we'll see. And Kant's Critique of Practical Reason, he also makes a similar point. He says practical reason is really about how should we live. That's what the thing is, and his critique of judgment is all about how to make these decisions. And this is very similar. It goes back to something called the Socratic turn. So Socrates initially thinks he's a scientist, and then at some point he comes to realization that he says I'm inadequate. He said I can't decide between these two. There's two different schools of thought. One, I think everything is ultimately constant, and other things everything's changing. It's Parmenides and Heraclitus. And then he makes this turn, and he realizes that the questions that he was actually asking about the world, about making sense of the world and his place in the world, they weren't the scientific questions. They weren't what causes what. They were something else. They were about how we should live. And this Socratic turn is really from thinking of himself as a scientist to thinking of himself as an engineer, in that broad sense of how we should live is a design question. I mean, I think of, how much time do I spend with my children? How much time do I spend at work? How much time, how should I treat other people? Those are all questions about how we should live, about design. And this Socratic turn is also, in modern terms, the pragmatic turn. Seeing that. Just a couple other real quick ones. There's a book. All engineers are not. 50 years ago, it was very common just to see engineering as applied science. But there's a whole enlightened group. Bugliarello has this article and saying it's a book, 1991, I think. Engineering is a Social Enterprise, and which influenced me. A very recent book, A More Beautiful Question by Warren Berger. This is all about, comes out of Silicon Valley thinking, how should we do things? And A More Beautiful Question comes from E.E. Cummings' poem. It starts, to have a more beautiful answer, you first have to have a more beautiful question. And in the way it goes is, why are we doing it this way? What if we did it that way? So it's all, they're asking questions about how, this is design. Why are we going with that design? Maybe it's a better design. And one of the third questions is always, well, how would you implement that? Okay, but those are things. There's a great book by Kevin Kelly. He really focuses on, God created us. Now we're creating, the technium, he calls it. It's this great book, I think I recommend. It's called What Technology Wants. I would have preferred it if he titled it What Engineering Wants, but it's pretty much the same thing. And just an example, this is a history of IBM, I think, making the world work better. Just an example of this type of thinking. Dewey, John Dewey, American Pragmatist, kind of summarizes where I am so far. And he says, we are participants in the construction of the good. So what engineers are is that's all of us. We're participants in the construction of the good. I think of pragmatism was an early attempt at engineering, philosophy of engineering worldview. Okay, so now we're more or less on time here. We're thinking. So part one, I introduce the engineering philosophy, which I've just done. Part two, now I'm gonna really get into engineering thermodynamics, and you'll see that engineering thermodynamics is engineering, and I would put it this way: engineering is thermodynamics, and thermodynamics is engineering. I distinguish it from Boltzmann, and then I'm going to go back and look at the history. Where did it come from? And then we'll get a better sense of what engineering thermodynamics is. So this is my guru, Peter Atkins. Oxford has a dozen books out on thermodynamics, textbooks as well as pop books. And I was reading this one in the second line. He's talking about this. He says about the history of thermodynamics is Carnot and Boltzmann epitomized thermodynamics. Carnot traveled thermodynamics from the engine, then symbolized by industrial society. Boltzmann traveled to thermodynamics from the atom, the symbol of emerging scientific fundamentalism. So the main point is he's pointing out there are two histories of thermodynamics, and there are two current versions. This is what shocked me. It's like, oh, thermodynamics still has both aspects, both versions. Yet these are not compatible. This is basically the Carnot, what I'm called the engineering thermodynamics version, and then the mechanical Clausius-Boltzmann version. So, I mean, theoretically, one of them is a special case of the other, maybe. I don't know which one's more general, which one's the right one. And I'm going to argue that engineering thermodynamics is more general, and it subsumes and supersedes all possible mechanical formulations of thermodynamics. Another guy who got this, a friend of mine kept telling me I should meet Don Cardwell, and I never got around to it, and then he died. This is a good thing. He says, almost traditionally, it seems, accounts of the development of concepts of work and energy have tended to describe them within the classical framework of Newtonian mechanics. I would like to suggest that this may be to take too narrow a view of the case. I love that. I would like to suggest that this may be to take too narrow a view of the case. It is to project backwards our present specialist arrangements of scientific knowledge, our present divisions between sciences, and to assure that past development was strictly guided by these divisions. And this is to make a questionable historical and sociological assumptions. So basically what he goes into is that the history that most of us got of thermodynamics was in fact based on assumptions of the mechanical versions. And so, must have happened this way. Carnot was a historical footnote somewhere. Maybe not. Okay, so I'm going to trace this back. The real beginning of thermodynamics, I'm going to suggest to you, comes from Leibniz. And he had a lot of friends in this, but in this proposed move from statics to dynamics. And Leibniz actually introduces the concept of dynamics into the discussion. And this stimulated something called the vis viva controversy at the time, or it was sort of going on anyway. But and what the question is what defines rational mechanics? They're looking for what is the basis of mechanics? Well, this depends upon what is conserved, energy, conservation of energy. But what is energy? There are two concepts of energy. One was mv, which is mass times velocity is momentum, and the other was mv squared. And the guys who were pushing this, you might think mv squared came from Newton. In fact, they claim it came from Galileo, which is plausible. Anyway, but Leibniz gives this enigmatic answer to this question of which is the correct concept of energy, and that would define the correct framework of mechanics. And he says both. And so this creates a new foundation for a more general theory of change. So all real change for Leibniz has these two opposite complementary components. You get a sense of this. It's sort of like wave and particle. It's like in quantum theory, you say, oh, well, De Broglie, every phenomena has both a wave aspect and a particle aspect. You may be looking at the wave looking at the waves, but there's a particle aspect there. Looking at particles, there's a wave aspect there. So this is kind of what, in fact, maybe quite literally what Leibniz is saying about MV and MV squared. Okay, so 50 years later, the vis viva controversy either reemerges or is ongoing, and this guy Maupertuis comes up with a kind of another version of Leibniz, he's very much accused of plagiarism, which is kind of nasty, but who cares? But he realizes that these two concepts of energy mean there are two different mechanics. And there are two principles of conservation, if you like. So what's the deal? So he, like Leibniz, Maupertuis' resolution is to say, well, they got to both be right. And he introduces this new concept of change. And for him, all change is an action. This concept of an action is central to him, central to thermodynamics. It's central to everything you'll see later. It's extremely important concept, and it's not. You can find a mechanical version of action as words used. This is one of the problems in understanding this stuff, is that people use different words to use same word to use to say different things. So for Leibniz and Maupertuis and later others, action is dualistic, composed of irreducible aspect of both mv and mv squared. Okay, so Maupertuis also has this engineering realism, as he calls it, and his favorite thing, partly because Euler says he's right about this, is the orbit. If you look at an orbit of a planet, it's an optimized balance of complementary components. So there's a linear mv, and the curvilinear mv, accounts for the mv squared. And a deeper thing here is lines and curves are incommensurable. You can't turn one into another. And this is an ancient recognition. It's historically the problem of the quadrature of the circle. Can you construct a linear polygon or group of polygons or whatever inside of a circle to get the area of a circle? And the answer is no, it's not possible to do that. So this lines and curves are incommensurable, and they're also co-defined. And any time you have co-defined opposites, it's typically called conjugates, they're always complementary. They're opposite, but they're related. An analogy, I think, is with particle and wave, but also local and non-local. Local and non-local, these are co-defined concepts. So they're going to end up being complementary. And complementarity ends up being pretty central to engineering. So the other thing that Maupertuis points out, he said, this regular orbit is like a solution to an engineering problem, okay, suggesting a reason or purpose for it. So I don't know, it used to be an old little app where you tried to launch a satellite. This is back in the Sputnik days, and you launch a satellite into a regular orbit. Well, it turns out it's not easy. You have to get it up and get it the right velocity, and then you have to inject it into at the right angle. If you don't, you get these really elongated orbits, and things come crashing in at about the third rotation. To make a regular orbit is really hard. That's a sense of an engineering solution. In other words, a regular orbit is a really carefully balanced optimization of these two things. Okay, so Maupertuis goes on to say that everything in reality is made up of these balances of things. Okay, and engineering solutions, if you like. Now, just to throw in, I'm going to give a different paper on this at the conference. Max Planck was, as they say, obsessed with Maupertuis' concept of action, because he realizes that what Maupertuis was talking about in action is also the same as what came up in his theory of quantum theory. You might note that what Planck did in his black body stuff is he integrated two opposite theories of light, particle theory of light and a wave theory of light, and somehow he put those together, and that's why he comes up with this concept of action. So anyway, he keeps saying, we really ought to go back and look at Leibniz' concept of action if we want to understand quantum theory. Okay, so most of the stuff that then went on after Maupertuis everything was around the École Polytechnique, which is, 18th century. École Polytechnique was considered the first engineering university. And basically, if you look at the Eiffel Tower, you look at there are these names inscribed around the Eiffel Tower. They're virtually all associated with the École Polytechnique, and almost all of them engineers. Okay, so here's my hero. Lazare Carnot. Lazare is Sadi's father, and I think he's the real genius in the family. Everybody knows about Sadi, but they don't know about Lazare. I only casually bumped into the awareness of Lazare, but then now I'm all over it. So Lazare's in his couple of different essays, but in his 1803 mature essays, he points out, he says, there are no engineers and no account of engineering in any possible rational mechanics. So he's kind of kicking, he doesn't like all this, what we call mathematical physics, but today, like, oh, it's all mathematical physics, it's all the universe is numbers. He was like, well, where are the engineers in that? Where's engineering practice? I don't think you guys are making any sense of that. This traces back to the idea of an engine too, but we'll come to that. So Carnot explicitly aims to develop a more general post-mechanical engineering worldview. And his dynamical engineering mechanics is what is later understood as engineering thermodynamics. And he explicitly says that he's trying to complete Leibniz's program. He's very much, sees himself as building on. Leibniz, he said, just never completed his program, so that's what I'm doing. And he has a formal argument, and this is that there's a well-known principle in engineering practice that we lose in velocity of time what we gain in power. That is really simple. I mean, it's, if I can use pulleys and I can raise a weight slower, and I have to with less strength. Okay. And what he argues is there's no rational, he hits on in the essay, he says there's no rational mechanical account of this principle that everybody knows. The other thing is what he's done here in adding velocity and time is he's added another dimension, and he's going to push us to a higher order conceptual framework. Now I get into that a little bit. So these are implications of what Carnot's doing. So one is that he's saying engineers have options in accomplishing a task. They can use pulleys, they can raise something more directly, so there's a time thing. And the fact that engineers have options means that they must choose between those options. So they're necessarily choosing, okay, which we've been over in part one. In other words, they're embodied in an existential situation. They are in an indeterminate possibility space, a potential space. And when they choose how they're going to go about raising a task, and do it, that's actualization of the potential space. So in a sense, as with Florman, engineers have a constrained existential free will. They're constrained by their own abilities and whatever the resources are, but they always have this openness. Okay, so what I point, hopefully a lot of you have had thermodynamics or familiar with thermodynamics. So in adding this time velocity dimension, he's moving us from a determinate to an indeterminate framework. And think of this in linear algebra, you guys are into that. It just means I have one more variable than I have equations. So at that point, I have an indeterminate situation. So, and what he's done here is he's moving us from the traditional idea of a path-independent transition, which are always determinate in classical mechanical things. I'm moving from one state to another state. I don't care what the time is. That's all those things. The path, it doesn't matter. It's path independent, state to state. And he's moving us to something saying, well, that's nice, but no. Reality is path dependent, and the situation is indeterminate. And so you're going from a possibility space of many options to an actuality space. And so I had to select amongst my possibilities, so to speak. So that requires a choice. So the actions or choices actualize the potential and bring about a particular historical future. I'm not going to get into this. This is an analogy to collapsing the wave function in quantum theory. Now I'm going to give a couple of images here. I'm going on time. I'm close here. So I'm going to give two images here. One, I call it Galileo's boat, an inertial frame. So if you all remember Galileo in his essays, he talks about, he's confronted with this idea of, well, what he wants to demonstrate is that if he's in a boat that's going in a straight line at a uniform velocity, and he can run experiments, dropping balls and doing all this sort of thing, and the experimental results are exactly the same as if he was on land. So he said, you can't tell the difference. If I'm in that boat, you cannot tell the difference. You cannot tell whether I'm moving or I'm not moving, okay? And so this is this inertial frame thing. You see, it's very similar actually to what Einstein does in the equivalence principle. You can't tell whether it's gravity or a rocket at the bottom of the thing. But I'm sorry, getting off topic here. So anyway, saying that this idea though is the inertial frame, and this is very basic to mechanics. But so Lazarin comes in. He says, well, what are the wind changes? Well, then, if the wind is changing during while I'm running my experiment, then when I drop the ball, it isn't going to drop straight down. That's a problem. And what if this steersman turns the ship? It's like I'm going in I'm adding a curvilinear. So Galileo's boat is going in a straight line, but what if it curves? What if the boat turns? Okay. Well, the experiments are not come out the same. So what Lazar and Leibniz are saying was like we have inertial and non-inertial frames, okay, if you like. Sometimes we're going in a straight line, and that's nice, and there's a whole inertial frame. We love that. But there's also other things go on. There's other accelerations that turn us one way or another. And so what Lazar and Leibniz are doing, they want a more general dynamics. In their dynamics, all change has both a linear and a curvilinear component. It has a linear, and they're not rejecting the other, but they're adding. They're going to a higher dimension where they want to add this other non-inertial stuff. Okay, second image I'm going to lay on. So two types of equilibrium. Static equilibrium is in statics. Okay, Newton's third law, every action has an equal opposite reaction. Linear opposites, if they hit, what happens? They cancel, zero sum, no change. In dynamic equilibrium, it's not the same, because the up and the down, if you like, are different. I mean, the back and the forth have complementary components, and so they don't cancel. Okay, they just keep going back, and they keep, if you like, going oscillating, cycling back and forth. And these cycles are net productive. That's a deeper point, but you can ask me about that later if you want. But anyway, so it's dynamic equilibriums are net productive. And I want to just suggest a little relation here between that ellipse there down at the bottom, that cycle, and the cycle in Soddy's attempt to understand the steam engine. Also, in the dynamic equilibrium, if these cycles, cyclic relations are fundamental and ubiquitous, which is what Lazar and Leibniz want to argue, then per hypothesis, maybe they help us understand or to make sense of things like harmonic oscillators. And in the pendulum example, Huygens was a big player in all this. With his pendulum clocks and everything. And you can ask me about that, but he's very, very important in understanding. For instance, when the pendulum is at its height, no kinetic energy, it's a positional positional potential. And when it's at the maximum kinetic energy at the bottom, that's a maximum maximum kinetic potential. So these are two opposite kinds of potential: position and momentum. Surprise. And a lot of this gets into Fourier was a good buddy of Lazar's and so forth. They're all in that equal polytechnique. The other part of it, I want to give you an image here of the Earth. This is the Earth is homeostatic, if you hadn't noticed. And this is what, everybody's worried about global warming and stuff. But the Earth has been in a pretty homeostatic state for at least 3 billion years, maybe more. And it's in a dynamic equilibrium somehow. So the way I like to put this is there's the CO2 producers and the O2 producers. And they have two complementary agendas. Okay, so each one feeds the other. The oxygen producers love CO2, and then they give off oxygen, and then the others do just the opposite. And so the Earth is in a dynamic equilibrium. The Earth is an engine, if you like, cyclic engine, and yet it progresses. This was the theme of Dorian Sagan and Eric Snyder's book Into the Cool. Okay, so we need when I argue here, we need a paradigm shift, but I've argued this is a meta paradigm shift. This is not a shift within mechanics. In other words, there are a lot of advances in mechanics, a lot of advances within science. Kuhn talks about these paradigm changes. What I'm talking about here is a meta paradigm change. In other words, we're going completely from mechanics or statics to dynamics, a completely different point of view, which is the engineering point of view, which I've been laying on you. and engineers in particular are participants inside reality. Dewey goes on and talks about the difference between spectator representation of inquiry, where we're detached observers trying to understand the laws governing objective reality out there, and versus being participants, where we're actually doing things inside. I'm going to finish off here quick. This idea of participatory universe is not, again, it's new. I call it Carnot's epiphany, is that we're engineers in a world of engineering. John Wheeler, there's a lot of stuff here. I'm going to give another paper, hopefully, at the conference about how all this applies to quantum theory. But Wheeler saw in quantum theory this actualization of the potential was it required a participant. I like this one quote, though, from Pauli. He said, "And in the new pattern of thought, we do not assume any longer the detached observer occurring in the idealizations of this classical type of theory, but an observer who by his indeterminate effects creates a new situation theoretically described as a new state of the observed system." So he's talking here about moving from a spectator to a participant view, which I think occurs. Why do we have where did the participant thing come in to thermodynamics? Okay, so a little summary here. What I hit here is that Vincenti was saying at the beginning, he said, engineers understand the structures and functions of reality, their intelligent purposes, in ways that purposeless science cannot. Scientists understand the why. Why do we have these winglets on the plane? Why do we put the engines where we put them? And what is it for? What's a plane for? And and if you go into the biology of this, you can ask all these questions. Harvey, what is the heart for? What does it do? And these are all questions. In biology, it's very obvious. It's not quite so obvious when people, and I guess more as people are looking at the ecosystem, you see that the way in which we're understanding reality is in terms of purposes and stuff. And then we go like, and then we want to reduce that down to, particle mechanics or something. That's the mistake. Somebody put it, so what we want to do here, if we take the biological as the paradigm, we're going to explain physics in terms of biology, not biology in terms of physics. Okay, so the primary ontology is biological, or if you like, the world made up of engines. And of course, what I want to point out here is that Leibniz is basically saying the same thing, which he calls a famous principle of sufficient reason. And it's a methodological principle. You want to understand something, you want to ask what was the reason for it. Okay, he wants to ask the why. And that's why both of them are doing this move to the more general framework, where this question of why or what for, the path-dependent question, makes sense, which does not make sense in path-independent mechanics. And his other big principle is the identity of indiscernibles. And what this was, I can't get into too much, but one of the presuppositions of the mechanical framework is the symmetry and uniformity, Noether's theorem, if you like. And what his response to these ideas of uniformity is, if it's uniform, then you can't tell one point in time from another point in time, one place in space or another point in space. And so he's really just saying, science is not going to cut it, basically. I think I should end there. I have some other stuff, some other summaries, but why don't I end there? Does that sound right, Christine?
Yes,
thank you.
Yes, there are a couple of questions in the chat.
Already, okay.
That's really great presentation, Terry, and it's great you bring a lot of history, philosophy, and all packed together to come to your thesis of like engineering thermodynamics probably is a better framework compared to the general science or physics, especially for a question related to life, evolution, and the economics. And I think a lot of us at thermodynamics kind of inclined to that thesis. And it's a great honor to have you here. And I see in the audience a lot of our patron from thermodynamics 2020. I see philosophers, Susan. I see Katalin. I also see Eric Tyson here, who have written a lot about the cosmic evolution. And it's really our interest to make these two interdisciplinary or the transdisciplinary people talk to each other. And we have seen over the years or over the century that the physics never gonna solve these questions like evolution, life. These are the questions beyond physics. And if you look at the recent history, like econophysics is there for over 25 years now, but it has no clue like how to handle economics in terms of physical science. Therefore, I truly believe the thermodynamics has a potential here. Like Terry, you have brought like it has some option and the value system that engineering thermodynamics encompasses by its design. That's the aspiration of us at thermodynamics too. And with that, I will open this session for a question and answer. And I would encourage our participants to please unmute yourself and ask questions directly to Terry. I see there are some questions from Tia Everall. I'll greatly encourage to make it a little more interactive, and please speak up your question by yourself.
Go ahead, Tia.
Oh, in the beginning, you made a comment about that I guess engineering can't be understood by a scientific worldview, and I didn't understand if you were saying any scientific worldview or
so the scientific worldview. The scientific worldview is defined by two presuppositions, if you like, that you'll find. One is symmetry, and the other is conservation. And you see this. I mean, the interesting version of this. I don't know if you're familiar with Noether's theorem. Emmy Noether's theorem. I don't know if you guys know that. Noether's theorem, she was a famous mathematician and so forth. And what Noether looked at mechanics and scientific worldview, and she pointed out that every symmetry had a conservation. So for instance, if I can't know if I can run these off the top of my head, but there's a linear momentum is conserved because there's a type of symmetry. There's an angular momentum is conserved because of a different kind of symmetry. The fact that time moves forward uniformly means that energy is conserved. And so this is another theorem. So, and you find that, and it's a sophisticated version, if you like, of the idea of inertial frame. And as long as you have an inertial frame, then the mechanics works, like in Galileo's boat. Everything works as long as I'm inside of my inertial frame. And so this problem with the scientific worldview is that it presupposes that frame. And I think that's a serious problem for evolution. I mean, this is where when Hubble, sees that the universe is expanding, this is a problem because it meant that the universe had a history. Well, if you have the symmetries and so forth, this uniformity of time, it shouldn't have a history. It should be the same all the time, time, space, invariant laws and so forth. I mean, I could go on about this, but I mean, does that help at all? I mean, just.
Yes, it does. It does. And my other question was, you talked about these constraints on engineering and the relationship to science. I guess you're just saying that there's lots of other constraints, and that's what this free will is. They're not just from science. There's like, design issues and cultural issues, and ergonomics talks about the relationship between the human body and the devices around it, and those are choices that are not necessarily connected to scientific principles, but are larger constraints. I guess that's part of what you're saying.
Yeah, there's a really messy problem in all of this, and that is that we use the same word in the engineering context and in the science context. The real context, is the engineering context. That's where we're all talking. Like we don't talk in science. We're all engineers. We're in that engineering. We're communicating with each other. We're raising questions. I mean, the whole idea of a question, I don't know, it doesn't make any sense in science. The scientific worldview, I mean, what's inquiry if everything's deterministic? I mean, it just doesn't make any sense. So you get, there's a famous, my friend Stephen Hawking had a deal. He said, I've noticed that people who are promoting predestination and determinism, he said, I noticed that they still look both ways when they cross the street. And he just points out there's kind of like uncomfortable hypocrisy going on in the scientific worldview. And the problem has been, still is, I have a lot of friends who have been pushing this stuff. And the problem is they're stuck. They know, just like Hawking, that there's some sort of problem, hypocrisy going on here, that we really do make choices. We are free will. But I mean, but how can you make sense of science, of the success of science and all that sort of stuff at the same time? How can you do that? And they're stuck. So they go like, oh, well, the Tegmark, it's all mathematical and all that sort of stuff. But they know there's a bigger picture. They just don't know how to get there. And that was me too. I mean, I struggled with this for a long time. And a lot of people just, how can you get away from the deterministic implications? And part of Noether's thing has to do with induction. They say, well, you have to have induction. I mean, I can do Galileo's experiment, dropping balls in Pisa in 16, whatever it was. And I can do the same experiment in Oregon here where I am, 2022, same experiment, right? Well, yeah, in some sense it is. And the fact that I can make that, the fact that there is that uniformity needs to be accounted for. The difficulty is if you extrapolate that type of uniformity and say, oh, this is representative of all phenomena and all structure in the universe, that's where you get into trouble. And what the engineering view is able to do is to have this idea that of seeing science. In fact, science isn't one thing, if you hadn't noticed, that science is picking out certain aspects of reality, but the bigger reality, if you like, how to put this, the reality is not the inertial frame in which everything would be uniform like that, where induction would work wonderfully for everything. And what you realize is there's a non-inertial aspect to this too. Leibniz, incidentally, in that identity of indiscernibles, kind of goes after this uniformity thing. And he says, my intuitive way of getting at this, I imagine we all believe that every point in space is unique and every moment in time is unique in some sense. At the same time, if we just take that as representative, the uniqueness, then we're not going to be able to make any inferences at all. So what Leibniz wants to do is he said, no, every point in space has these two components. Okay, and I mean, there's a sameness to it. Like yesterday and today, they're the same, but they're different. Okay, so it's trying to resolve that, and the scientists are concerned with the sameness part of it. And that's nice. But if they say, oh, and that's representative of everything, then that gets us into difficulty. So how do you get out of that? So that's where, when I went to the engineering worldview, I got like, oh, wait a minute, here you go. There's a way to see this as a, science as a sort of limited, I don't want to say limited special case. It's more sophisticated than that. I would say to some friends, if this was an easy problem, it would have been solved a long time ago, because thermodynamics has to come into it and these various ideas. Anyway, so I hope that helps.
That's really great insight, Terry. Like anything that evolves is probably not inertial, and science has been doing a patchwork on how to handle that. They come up with the kind of like inertial forces and try to handle that. And that's the reason I believe that the science has not been able to go from that living to non-living to the living science. Therefore, that's where the thermodynamics find its niche, and I really appreciate that. And my own research kind of indicates that anything evolving is a non-inertial frame, and then to handle that, probably the existing framework of science is not enough, and probably the thermodynamics can complement on that arena, and together probably, hopefully within this century, we can understand life better.
Yeah, you guys say the one thing I mentioned in there's this movement from seeing the world and probably in order to understand evolution, to throw in this chance factor, this probabilistic thing. Steve Gould goes on about this. What if we were to rerun the history of the biological world? This is in his book, The Wonderful World. And he said, what do we, if we reran it, well, for the Darwinian process, we need to have new things coming up. Well, what are the new things? If it's all mechanical, unique to unique, we don't have it. So he has to have some sort of chance thing in there. Oh, mutations, chance mutations, Well, the difference in the engineering view is that you move from this probabilistic idea of accounting for the history of how the thing evolves. Instead, this is Leibniz, because they're asking why this particular outcome occurred rather than another one. Okay, because there are many, many possibilities. Stuart Kaufman, many of you may have read his stuff. He's talked a lot about this. And Stu talks about
open this floor for a question, because there are so many people who has spent.
Well, let me just say the last thing. So Stu talks about there being 20 billion possible proteins. Why did we get the ones we got? Well, the idea in engineering is they are the ones that came about for a reason, and it's not because of survivability. Anyway, I'm sorry, I'm rambling. Go ahead.
No, that's really great. I thought, Terry, let's give our patron time to speak up. And I see here people in the audience list who have contributed, like you, a lifetime in understanding this puzzle.
So does Vincent want to come at me?
Looks like Kathleen, do you have any question for Terry? Kathleen, you have worked a lot in thermodynamics and the different idea, extropy, and I'm just curious, how that framework see evolution in the context. Looks like she's mute now.
There's something in the chat by Vincent. Do you want me to respond to that one?
Yeah, please. You see something, please do that.
So another thing that comes out of this. So the Clausius, in trying to interpret Soddy's original thermodynamics essay, I had a quote from him, but it's basically, he says, Soddy's brilliant. He comes up with this wonderful stuff, but of course he's totally wrong, because Soddy says something about the energy, the energy at the beginning and the end is the same. And he said, well, that can't be right. You have a certain amount of fuel and you burn it and you get work, and that's the end of it. And the point of that is, I have a kind of essay called From Carnot to Clausius and Back. And the main thing to realize is that they're talking about two different things. I mean, they're different. And the whole, thing about, the idea of entropy has just been a mess, if you like. If you guys, anybody who's worked in thermodynamics knows that concept of entropy is I don't know, somebody listed there's 20 different definitions that are around and stuff like that. And it's kind of a mess, because the basic model of what is a process and what is an engine and how does work occur is very different in Soddy than in Clausius. So one of the guys that I really like is a guy named Steve Klein, who's an engineer at Stanford, and he had a couple of nice things. He said anytime you're talking about, when you're discussing thermodynamics, he says if anyone brings up entropy, he says shoot them. And let me give you one other anecdote. My friend Robert Ulanowitz, you may know, and I've talked about this with Ulanowitz about thermodynamics. Well, there's two different versions of thermodynamics, And he says, oh, let me tell you, when I was getting my PhD at Johns Hopkins what was it I can't remember. Anyway, he said, I get the obligatory thermodynamics question. And he said, obligatory thermodynamics. He says, I'd said anything about particles moving around and so forth, he said, rather than the engineering version, which is different. He said, I would have been out on the street it was chemical engineering. He was going to be obligatory thermodynamics thing. So the point is what he's saying is you're not likely to get a real strong hearing about Boltzmann's thermodynamics. They have a process concept of thermodynamics, which goes to work and so forth. So these concepts, the point of this anecdote is that is to confirm what Atkins is saying. There are two current versions of thermodynamics that are out there. And the one that is the engineering one is alive and well. I was at Caltech one time and I went into their bookstore and there were 8 different books on thermodynamics. And I spent a day going through them. And what you find is that, 4 of them favored engineering thermodynamics and 4 of them favored the mechanical thermodynamics. They both mentioned each other, but the dominant theme in each one, was, for the mechanical thermodynamics, they saw, engines, oh yeah, well, I don't know what those are, but, we don't really care. And the engineering thermodynamics is saying, yeah, well, Boltzmann, there's something to Boltzmann and, all that sort of stuff, but that's not really what's primarily important. So
Just
there
to
are these two
clarify-
versions.
Just to clarify your comment about entropy theory, like I see entropy as a kind of constraining force. Personally, and that's my personal opinion, and it has a
We'll
role
add that to that number 21. Yeah.
Yeah, like it's a role to play. It has a role to play in kind of opposing force in some sense, but it's not the general statement. And I hope this great group of people working on this can put this idea in a very simplified form and kind of can present this idea in a more cohesive form. That's what we are trying to do, kind of theory, like you brought a lot of history, philosophy into the things, but when we have to teach our student, we have to simplify it and kind of put it together in a form they can understand, and in a form it makes sense to them. And that's something we have to accomplish over the years, and that's I think a part is missing. We have seen it from the physics people, we have seen from the economics people, even econophysics people. I see in the audience Professor Dowija from Poland. They are trying very hard to kind of bring economics from a thermodynamics perspective, but I believe that over the time we'll make it simple in a term people can easily understand, and will be practical, that can predict and kind of also solve some problem we need to solve as a science. And that's the direction we are heading to. And that's a great step, and bringing all these history, philosophy into the equation. And if anybody don't have a question, then probably I would like to take it towards the end. Before that, I would like to request Terry for your few final words to us who are working on this thermodynamics framework to kind of unified knowledge, unification of knowledge.
Yeah, can I just, one thing, there's something in the chat from, I think it's Vincent, and he's talking about the entropy of the universe. I just give you an example. You talk about, well, what's practical we have to do. In cosmology, so Sean Carroll has a great book. Sean Carroll's at Caltech. He has a great book called From Eternity to Here. And it's one of the best treatments of the questions of entropy and probabilistic account of thermodynamics and so forth that's around. I highly recommend it. But one of the things that he points out, and others point out, he said, if you just came across a universe like ours with a certain number of particles and moving around, stuff like that, so what would be the most likely state of that universe? So it would be equilibrium, not just maybe, not just a little bit, but overwhelmingly the most likely state of a universe is equilibrium. So wait a minute, what kind of universe are we in? We're in a universe that is not in equilibrium. And the worst problem is the idea of the low entropy beginning. So entropy is always increasing. That's the kind of like, oh, entropy always increases. So if entropy always increases, how do we get a low entropy beginning? And I want to suggest to you that not only don't we have an answer for that within that version of thermodynamics, we don't have any possible answer to that. Okay, there's no possible answer to this. There's a thing called Loft-Schmidt's paradox too, which Boltzmann was aware of, and basically talks about this time. I mean, it also means that the universe had to come from a different state, so forth, to get to the low entropy state. I mean, there's just no account of this. It doesn't make any sense. I gave a talk in St. Petersburg a couple of years ago about the entropy thing too. And the other thing is, like, if you look what happens, so let's say we start with this low entropy thing and the energy spews out, entropy increases. What happens? What we actually see is the formation of stars. Now these stars, what should be happening is less possibility to perform work. The gradient of the universe should be going down, right? What happened? We see the formation of stars that are like 6,000 degrees, or some in the corona, they're like 1,000,000 degrees, and they're sitting in an environment that's like 3 degrees. And this is incredible gradient has been created. These are like the possibility of performing work has just gone up. So every place you see a star, you see an increasing gradient. So the actual history of the universe that we see, we don't see this spewing out of dispersal of energy or whatever it is. In fact, we see things like formation of stars, and then the stars are doing that. Another thing I was making, the one in St. Petersburg was about the formation of elements. Okay, this is another funny thing. So here in these stars, with the current theory, they burn, the hydrogen and the so forth and helium or whatever they got, and then they collapse down in these.
That's really great. I look forward to reading that book. And
they blow up. Wait a minute. They form in 15 minutes they form all the elements up to iron, and then they spew them out into really this super cold, zero vacuum space. And the nice thing is they don't fall apart.
Mm-hmm.
That's weird.
That's really great insight, Terry. I look forward to reading that book. And if there are not any more questions, I would like to conclude this presentation. And I look forward to meet many of you at the Thermodynamics conference, and probably we'll make one more announcement about the pre-conference very soon. And thank you so much for your effort to connect sciences. And I strongly believe that together we can connect sciences and take our sciences to the next level. Thank you so much. Bye-bye. Thank you, Pierre. Thank you, everybody. Thank you, Asuka, Vicent, Marek. Thank you very much, Terry. That's a very great, insightful talk. Thank you so much.
Okay. Hopefully made sense. Some of it made sense to some of them.
Yeah.
Yeah, thanks.
Okay.
Pierre, you could make it. Thank you.
I'd hang on if you guys got questions.
Mm-hmm. Yeah.
Yes, I've noticed that, I'm sorry, I cannot pronounce your name. You've unmuted for a very long time. I didn't know if you had a question. I'm sorry.
Marek, do you have any question for Terry, Marek Franokovich?
Absolutely. So as for now, I have no questions, but the topic is very interesting, but it would be the topic for longer discussion. We are very interested in all these problems, especially thermodynamics, irreversibility. For example, I worked for some time with Prigozhin in his group, on non-equilibrium statistical mechanics. So I was also involved in problem of irreversibility. And now we are also working at our faculty in Krakow on connections between arts and sciences. So here I am very grateful to Terry to add this third dimension of engineering, because just we want to create a kind of community of artists and scientists. So also we'll add engineers to discuss how we shall approach reality. So in general, the problem, when I look at this, so I see that first we have a kind of processes, phenomena we observe. For example, stars, we observe reactions and so on and so on. And we try to describe them. And as it was shown that it is impossible to describe all these things in precise and, let us say, ultimate way. So we try to coin some terms in order just to describe at least parts of this reality. So therefore, when we speak about energy, entropy, and so on, so these are some terms we use to characterize at least some processes. but it will not give us a kind of final picture. So therefore, for example, when I think about physics, so physicists try to just have a kind of models, kind of vision, use some basic terms to construct reality. And from my point of view, it was always something like other way around. That means there is a reality and we try to describe this. So for example, when I was a graduate student or postgraduate, I studied many articles about status of irreversibility. So people write a lot about irreversibility, but for me, irreversibility is just a kind of phenomenon. So for example, maybe it is just, like idiot or pedestrian approach to the problem, but when I see all these arguments concerning irreversibility, for me it's a bit artificial, because I assume, for example, that something is right. Like, for example, classical physics or quantum physics is right. So because of this, we shall be able to explain irreversibility using these terms, these theories we have. Yeah, but theory is only a part of reality. So because of this, if we look just like here, it was presented, if we look at processes, yeah, if we look at some phenomena and so on, we try to just to explain it, to see them, to try to, for example, propose some kinds of language, different languages, maybe just connecting different approaches, engineering approach, scientific approach, arts approach, and so on. So then we are closer to the understanding, because our ultimate goal should be to understand what is happening around us. We know that we cannot understand it in a perfect way, but anyway, in a kind of iterative way, we can approach to this understanding. So therefore,
Yeah,
what
very
I
good.
heard, it was very interesting.
Okay, well, a couple of comments. So I was fortunate. I spent some time with Prigogine. He was in a lecture series that I organized, and I quite liked him. And he actually wrote a reference letter for me at one point. But so I'm really sympathetic to everything he was doing. But the way I put it, I really talk to you more in future about America, about your efforts in bringing together the sciences and the arts, because that's, for me, that was one of the things. I don't even think I was going after it. I mean, I kind of maybe assumed it was there, but to see that in engineering, that the value component is naturally in engineering and the technical stuff is naturally in engineering, and they're together. I could give you a bunch of references, but one you might look at in particular is a woman, colleague, her name's Shannon Valour. It's Vallor. Shannon Valour. She's, I think she's up in Edinburgh right now, the Edinburgh Futures thing. And what's the name of her book? I have to look. You have to look at her book, but it's about engineering and virtues. And she and I both gave talks at a conference in China, and we bonded at that point. So she's very, very smart and very much on the question of what I call the value context of engineering decisions. When you're making an engineering decision, you're not just an applied science. There's a famous essay by a guy named Dupuit, D-U-P-U-I-T. It's a French engineer, and it's an essay about should we or should we not build this bridge, and what kind of bridge should it be? And so it puts the question of the engineer's question in this social context, in an economic context. What's the value of this bridge? It's going to connect two different economic areas. It's a brilliant essay, but it's a kind of famous essay. Some book out somebody just put out recently. I can't remember about that. I'd also recommend Steve Klein. It's K-L-I-N-E. He's a guy that said, shoot anybody who brings up entropy. He and another guy, Peter Corning, who I recommend, is very big on this idea of synergy as being, what is it that guides the engineering decision? And the idea is that you're guided towards a win-win thing. You want to expand your possibility space. You don't want to narrow your possibility space. And one of the ways that the possibility space expands is through synergy, through these synergistic interactions. He and Klein wrote I think it was 2 essays that completely dominated 2 issues of a particular journal, and it's called Thermoeconomics. And I think it's brilliant.
That's great. And I see
So,
in the
yeah,
audience.
I look forward to talking to you more, Merrick. If you want to, email me or anything, we can do that.
That's great. That's great connection. And thank you so much for all those insightful talk. And we look forward to learn from you again at the conference. Thank you so much. And with that,
Yeah, kudos again. Kudos to you, Ram, for putting this together and for all your work on this. I think it's amazing. And as you and I had talked yesterday, I think you really have a good vision of how to foster these dialogues. And I agree with you. There are a bunch of old guys like me who worked on this stuff for 50 years. And a few of us think maybe we have some good insights. And to share, in the last 10 years, I probably read more in the last 10 years since I'm not teaching full time than I had read in the previous 30, 40 years. And putting all that stuff together, and really, I hope I can share that with you guys on how all that fits together. Anyway, I think kudos to you, Ram, for facilitating this and having you the great vision.
Send that to me through email, and I'll be able to send it to all participants. Thank you so much. With that, we conclude this pre-conference series by Terry Bristol. Thank you so much. Bye.